In this lecture video, we're going to do a review of the general principles of hypothesis testing. Now, the overall idea in hypothesis testing is that we formulate opposing statements about the population of interest. These statements are called the null and alternative hypotheses. We obtain a sample from the population and we study the sample using the descriptive statistical techniques that you learned in your first methods class. Now, if the observed real-world data are inconsistent enough with the assumption expressed by the null hypothesis, then we may choose to conclude that the null hypothesis is in fact false and that the alternative hypothesis is true. Now, the question is, how inconsistent do the observed data have to be with the null hypothesis in order to lead us to reject that null? Now, the components of an hypothesis test consist of the hypotheses, obviously, a test statistic, which will be used as a measuring stick of reality, a rule for evaluating or assessing the observed value of the test statistic, sample data from which the test statistic will be calculated, and then a conclusion regarding the hypotheses. Now, a hypothesis test consists of a set of hypotheses that are stated in terms of one or more population parameters of interest. As we said before, the two hypotheses are the null hypothesis and the alternative hypothesis. Now, the null and alternative hypotheses are constructed in such a way that they are opposing statements or opposite statements. In other words, they are logical complements of each other. And so exactly one of the two statements is true. The null hypothesis is denoted H sub 0. This is a statement about one or more population parameters that usually represents the status quo, that treatment or intervention has no effect, or that there is no difference between populations. The alternative hypothesis is denoted by H sub 1 or sometimes by H sub A, and it is a statement about one or more population parameters that usually represents what the researcher would like to prove, that the treatment or intervention does in fact have an effect, or that differences exist between populations. And as we said before, the alternative hypothesis is the opposite or the logical complement of the null hypothesis. And so when setting up hypotheses, one of the main questions that students often ask is how to set up the hypotheses. And the primary way that we want to think about this in setting these up is that we identify what the researcher is trying to prove, and we always put that in the alternative hypothesis. All right, so typically a researcher is trying to prove that a new treatment or a new intervention that they've developed does have an impact, has a positive impact. They're trying to show that two or more populations are different with respect to certain parameters, and so forth. And so what the researcher is trying to prove goes in the alternative. Another way to think about it is that the equality statement regarding populations, or the statement of no impact or no effect, again, that goes in the null hypothesis. So that is, those are a couple ways of thinking about how to set up the hypotheses. Then we have a test statistic. This is a value computed from a sample that is used in the decision-making process. It's a random variable that varies from one sample to the next. All right, and it is, again, our measuring stick of reality. Then we have the rejection region, also known as the critical region. The rejection region, or the critical region, is the set of values of the test statistic for which we will conclude that the null hypothesis is false, and therefore that the alternative hypothesis is true. You'll remember that the null and alternative hypotheses are logical complements. so that exactly one of the two statements is true. One and only one is true. So if the null hypothesis is true, that means that the alternative is not true, and if the null hypothesis is false, that would imply that the alternative hypothesis is true. And so in performing hypothesis tests, the goal, what we're trying to do, is to show that the null hypothesis is not true, and therefore that the alternative hypothesis is true. And so this rejection region is identifying those values of the test statistic, which, remember, is our measuring stick of reality. All right, it's the set of values of the test statistic which will lead us to reject the null hypothesis and conclude that the alternative is true. And with that in mind, and an analogous way to think about it is that the rejection region is the set of values of the test statistic that are so inconsistent with that null hypothesis at a specified level of significance that the null hypothesis really becomes untenable. We really cannot continue to hold that the null hypothesis is true when we have a value of the test statistic which falls in the rejection region. And the reason is because the value of the test statistic is so inconsistent with that null hypothesis that it is just really not tenable. Now, in order to determine the rejection region, we need to know how the test statistic behaves specifically under the conditions of the null hypothesis. That is, when the null hypothesis is true. In other words, we need to understand the sampling distribution of the test statistic under the conditions of the null hypothesis. Now, you'll remember from your first methods class, you covered the basics of probability theory, and then after that you looked at sampling distribution theory. And the purpose of covering sampling distribution theory is because it provides the linkage between the descriptive statistics part of the course and the inference, the statistical inference part of the course. The sampling distribution, or the concept of a sampling distribution, provides a way for us to understand how a test statistic behaves if the null hypothesis is in fact true. And it is the sampling distribution of the test statistic under the conditions of the null hypothesis from which we come up with the rejection region. The next component of an hypothesis test is the sample data itself. And so that typically involves either a random sampling from one or more populations if you're in a sampling context, or the random assignment of treatments to experimental units in a experimental type of situation. Now, again, you'll notice that in each of these two situations, we see the word random sampling and random assignment of treatments to experimental units. And it's this randomization that provides the probabilistic framework required by the statistical test that we use. The other purpose of randomization is that it eliminates researcher bias, at least in the allocation of treatments to experimental units or in the selection of observations from populations. And so randomization is very important for both of those reasons. Now, this last bullet point is very, very important for us to understand and keep in mind. The specifics of the sampling procedure or the randomization process affect the probabilistic framework. All right? So again, the randomization provides that probabilistic framework required by the statistical test. That randomization and that probabilistic framework is what gives validity to our statistical procedures. And the manner in which we sample, randomly sample from a population, or the manner in which we randomly assign treatments to experimental units really determines that probabilistic framework. All right? And it's the probabilistic framework that determines the appropriate method of analysis, the appropriate statistical model, and the appropriate analysis of that model. And so we must take into account the specifics of the sampling procedure or the specifics of the randomization process in order to perform an analysis that will give us valid results. And then finally, the last part of the hypothesis test are the conclusions. So we would typically state those conclusions, or at least think about them and identify them in statistical terms. In particular, in terms of the population parameter or parameters that were involved in the hypotheses. But then we don't leave it there. We go beyond that and we state the conclusions in the language of the original problem, which will be in some applied area. And so the steps involved in an hypothesis test. Number one, we state the null and alternative hypotheses. We determine the appropriate test statistic to use and write out its formula. We determine the rejection region and write out the rejection rule. All right, and steps 1, 2, 3 are really can be done without having data. In fact, these should be done before even performing the experiment. If you think about the protocol that one might write for a scientific study, for example, a protocol for a clinical trial, or a more specific document in that context called the statistical analysis plan, all of these, the first three things here would be done before the study ever starts. In fact, in order to get approved, there has to be in place a protocol which talks about the project in general and the particular context in which the clinical trial is being done. But as part of that, there's also a statistical analysis plan that frames all of the questions to be answered and the analyses in statistical terms. And so this is all done before the experiment is even conducted. But to go beyond that, obviously, we have to have sample data. And so that leads us to step number 4, collect the sample data and calculate the test statistics. So again, we're either going to be sampling from one or more populations in a sampling context, or we're going to be performing a designed experiment where we have randomly assigned treatments to experimental units in some fashion, and then we have taken that design of the experimental design in mind, and come up with the appropriate analysis, which we've defined up in step 3. All right, and so then we collect the data corresponding to the plan. Now, if things happen in the context of the experiment that change how the sampling is done or impact the design of experiment, then obviously changes would need to be made in terms of the analysis plan. Okay, and then finally, once we do that, then we draw conclusions based on the observed data or the observed value of the test statistic in conjunction with evaluating that using the rejection rule. Now, statistical analysis is used in the context where we have to make decisions in the face of uncertainty. All right, and so that certainly applies to any scientific kind of decision making, but also in business and other areas as well. And when we are making decisions in the face of uncertainty, we can never ever be 100% sure that our conclusions or decisions are correct. All right, that's just that's not a knock on statistical methods. That's an acknowledgement of the reality that we face whenever we are trying to make decisions in the face of uncertainty. And it's in those kind of contexts where statistical analysis is actually developed for that, making decisions in the face of uncertainty. So that is one of the advantages and great things about statistics, is that it allows us to make decisions in the face of uncertainty. But we do realize that in that very context, or a defining characteristic of that kind of a context, is that we can never be completely sure that our decisions are correct, at least not at the time that the decisions are being made. And so with that in mind, in making decisions in the face of uncertainty, and in particular via hypothesis testing, there are four possible scenarios that can occur. The first scenario, is case one, is that the null hypothesis is in fact true, and our conclusion based on the data is that we conclude that the null hypothesis is true as well. In other words, we fail to reject the null hypothesis. Now, in this particular situation, we have come to the correct conclusion, haven't we? Because the null hypothesis is true, and we've concluded that it's true, or another way to say that, we have failed to reject that null hypothesis. Now, the second case, the second scenario, is that the null hypothesis is true. However, our conclusion based on the data is that the null hypothesis is false. Now, if the null hypothesis is in reality true, but we conclude based on the data that we get that it's false, then obviously we have come to the incorrect conclusion. Now, rejecting a true null hypothesis, concluding that the null hypothesis is false when in fact it's true, is called a type 1 error. All right? So this is obviously something that we would not want to have happen. So for example, if an example of a type 1 error, suppose we're doing a clinical trial to determine the efficacy of a new treatment for some ailment. If the new treatment is not effective, or maybe we're comparing it against the current accepted treatment, so if the new treatment is not better than the existing treatment, but we conclude that it is, then we have committed a type 1 error. So that would be an example of a type 1 error. The third situation, the third scenario or case, is that the null hypothesis is in fact false, but based on the data, we conclude that the null hypothesis is true. Now, if the null hypothesis is in fact false, but we conclude based on the data that it's true, then again we have come to an incorrect conclusion. But this is different than the previous type of error, all right? So we give it a different name. This is called a type 2 error. So an example of a type 2 error, let's use that same example of a clinical trial where we're trying to evaluate the efficacy of a new treatment for some ailment. So in that kind of a situation, the null hypothesis would be that the new treatment is no better than the existing treatment. Now, if that is false, or a type 2 error in that context would be that the new treatment actually is more effective than the existing treatment. However, based on the data, we conclude that it's no better. And that would be obviously something that we want to avoid as well. So we have these two types of errors, type 1 errors and type 2 errors, all right, that both are undesirable and we want to avoid. And then finally, case 4, scenario 4. In this case, the null hypothesis is false, and based on the data that we get, we conclude that the null hypothesis is false. So that would be another instance of a correct conclusion. An example of this kind of situation would be if, in our clinical trial example, if the new treatment is in fact effective, and based on the data we get, we conclude that it's effective. So that would be a desirable outcome. You know, if a new treatment is effective, we want to identify that it's effective, and not only that, we want to identify the magnitude of how effective it is. And so this is a situation where we would certainly want to be able to draw a correct conclusion. So those are the 4 scenarios, and I have a two-way table that really shows these. So the possible decision-making outcomes. And so here for the columns, I have the true state of the null hypothesis. The null hypothesis is either true or it's false. And so when setting up the hypotheses, and in particular the null hypothesis, we need to make sure that we state the null hypothesis in such a way that it is either true or false. All right. Then for the rows, we have our decision about the null hypothesis. And so we're either going to conclude that the null hypothesis is true, or we're going to conclude that it's false. Now, technically, we can never prove that the null hypothesis is true, and we typically avoid this kind of statement, but I'm using the word true here just to be economical in how I'm labeling these rows. Another way to say this, and a better way to say this, would be our decision about the null hypothesis. It would be, for this first row, we fail to reject the null hypothesis, and in the second row, where we reject the null hypothesis. Now, if the null hypothesis is true, and we fail to reject that null hypothesis, then we have come to the correct conclusion. If the null hypothesis is false, and we conclude that it's false, then again we have come to the right conclusion. On the other hand, if the null hypothesis is true, but we conclude that it's false, then we have committed a type 1 error. And finally, if the null hypothesis is false, but we conclude that it's true, or in other words, we fail to reject the null hypothesis, then we have committed a type 2 error. So this is a nice way to organize this information and organize these 4 scenarios. All right, it gives us a good mental picture of those scenarios. Next, let's talk about characteristics of hypothesis tests. All right, and so let's consider this, what turns out to be a conditional probability. In particular, the conditional probability that we conclude that the null hypothesis is false, given that the null hypothesis is true. Now, this event, concluding that the null hypothesis is false when it's true, you'll remember, is a type 1 error. Okay, so concluding that the null hypothesis is false when it's true is a type 1 error. And so we understand that in any real-world hypothesis testing or decision-making situation, there's always going to be the probability or the possibility of committing a type 1 error. And so, and also there's always going to be the possibility of committing a type 2 error before we conduct the experiment. And so, and those will be based on the data that we get in performing the experiment. And so we acknowledge the possibility of both of those types of errors, and in order to evaluate the quality of an experiment, we need to think about the probabilities of those possibilities. And so that's what we're doing in this slide. We're defining some notation for the probabilities of those events. And so for the conditional probability of a type 1 error, essentially, we're going to use the notation alpha. So alpha is the probability of a type 1 error. And then the event, we conclude that the null hypothesis is true when, in fact, the null hypothesis is false. Well, if the null hypothesis is false and we conclude that it's true, that's a type 2 error. All right, and so beta is the probability of a type 2 error. So those are the 2 primary characteristics of an hypothesis test, alpha and beta, the probability of a type 1 error and the probability of a type 2 error, respectively. Now, alpha has another name. It's called the significance level of the test, the alpha level of the test. And you'll remember that as the researcher, as the decision maker, you are the one who chooses the alpha level or the significance level that you want to use for the test. The significance level is really a measure of evidence that you're specifying to use in your decision-making process regarding the hypotheses. Now, another characteristic of an hypothesis test is the power of the test, which we'll denote by lowercase Greek letter pi. And this is the probability of correctly rejecting the null hypothesis, in other words, concluding that the null hypothesis is false, when in fact the null hypothesis is false. And so if I go back to this two-way table here, so in fact, let's look at the next part of this. And so we were characterizing the decisions, whether they were correct or whether they were errors, in this first slide here. Now we're assigning notation to the probabilities of these events. And so we see here that the probability of concluding that the null hypothesis is false when in fact it's true is alpha, and the probability of concluding that the null hypothesis is true when in fact it's false is denoted by beta. And then the probability of rejecting that the null hypothesis is false when in fact the null hypothesis is false, that is power. Okay, now the columns add to 1, right? And that's clear from these two entries here. 1 minus alpha plus alpha obviously is 1. And in fact, the way that we know this is because based on properties of these conditional probabilities, that the columns must add to 1. And so that is shown here for the relationship or the constraint between power and beta. All right, this shows that the power of a test is equal to 1 minus beta, and so that implies that beta plus power is 1. And so that's where we get, that's how we know that these two entries here have to equal, the sum have to equal 1. Now, the reality is that both power and beta are functions of several quantities. They are functions of the true values, of the true value or values of the parameter or parameters that we're testing hypotheses about. They also depend on the significance level used, the alpha value used. They depend on the sample size. They depend on the variability that exists in the population or populations. And so that while I'm just writing pi and beta as what looks to be just real numbers or scalars, they're actually functions of those different characteristics. But for ease of notation, all right, I'm suppressing the various quantities that they're functions of. But for a given setting of the various things that they depend upon, they do have this relationship. So those are important characteristics of an hypothesis test. Now let's look at relationships between these test characteristics. And so, for starters, for a fixed sample size, alpha and beta are inversely related. That is, if alpha is decreased, then beta will be increased, and vice versa. If alpha is increased, then beta will be decreased. And I'm stating these in this way, talking about if alpha is increased or decreased, because remember that as the experimenter or as the decision maker, the consumer of a particular set of results, a reader of an article, for example, we are free to set whatever significance level we want to use. Okay, and so we have control over alpha. We don't have direct control over beta, because again, beta depends on not only the significance level, but it depends on the true values of the parameters that are being tested, the sample size, the variability in the population, and so forth. But we do have direct control over alpha, so we get to set that. But in general, the impact of alpha on beta is that if alpha is decreased, beta is increased, and if alpha is increased, then beta decreases. For a fixed sample size, beta and power are also inversely related. So if beta increases, that means that power is going to decrease, and vice versa. If beta decreases, then power will increase. And so if we put these two results together, we can come up with the relationship between alpha and power. For a fixed sample size, alpha and power will be directly related. That is, if alpha is decreased, power will be decreased as well. If we increase alpha, then power will be increased. Now again, power is the probability of correctly rejecting the null hypothesis when the null hypothesis is false and should be rejected. All right, and so we want the power to be as large as possible. We see here, however, that if we were trying to impact power just by alpha, how do we make power bigger? Well, by increasing alpha. But we have to remember that alpha is the probability of a type 1 error, all right? And that's something that we typically want to be fairly small. And so, you know, we have these competing issues here. We want alpha to be small, but we want power to be big, but they are directly related. And so if we choose to use a very small alpha, a very small level of significance, then we will be effectively reducing our power by doing that. So that's just something that we need to keep in mind. There's always going to be a balance between the size of alpha and the size of beta. And you know, in a given experimental situation or decision-making situation, we need to think about what does a type 1 error represent in a given situation? What does a type 2 error represent? What are the relative costs of type 1 and type 2 errors in a given situation? And then try to balance alpha and beta based on those kinds of considerations. So we've seen the relationship between alpha, beta, and power for fixed sample sizes, but as experimenters we have the ability, the freedom to change our sample size or choose the sample size that we choose to use within certain limits. Now, so we need to think about the impact of sample size on these hypothesis testing characteristics. Now, in doing this, we're going to, in this case, fix an alpha level. We're not going to specify it, but just consider the significance level alpha to be fixed. And so for a given significance level alpha, if we increase the sample size, that's going to decrease beta. In other words, it's going to decrease the probability of a type 2 error, and it will increase power. For a given significance level alpha, if we reduce the sample size, then that will increase beta. In other words, it will increase the probability of a type 2 error, and it will decrease power. So in general, for a given level of significance, when we increase the sample size, we are increasing the power, we're enhancing or improving our ability to detect when a null hypothesis is false, and we are reducing the probability of failing to be able to do that. We're reducing the probability of a type 2 error. And the reason this is the case from an intuitive standpoint is that as we increase the sample size, we're getting more and more information about the population from which we are sampling. Now, ideally, we would like the probabilities of committing a type 1 error and type 2 error to both be 0 and therefore power to be 1. But we know that in any realistic decision-making situation that alpha and beta are both going to be positive, and therefore power is going to be less than 1. Having said that, we would like both alpha and beta to be small, in other words, close to 0, and power to be as big as possible, or in other words, close to 1. As we've seen in the last couple slides, if we want to decrease beta and therefore increase power for a given or set value of alpha, let me say that again, if we want to decrease beta and increase power for a given set of alpha, then what we have to do is we need to increase the sample size. And so that is one way. Increasing the sample size, controlling the sample size, and making it large enough at least within the constraints that we have. So increasing that sample size will make beta small. For a given value of alpha, it will make beta smaller and power bigger. And if it's possible, we can get a large enough sample size so that beta can be as small as we'd like. Now, it'll certainly be positive. It won't be zero. It'll be positive. But if we can take a large enough sample, we can make sure that we'll have enough power to detect a given treatment difference. And that's the other thing that I need to throw in here. Remember that both beta and power are not constants. These are functions of a variety of quantities. The significance level, the true value of the population parameters that we're testing hypotheses about, the sample size, the variability in the population, and so forth. And so when we're talking about have a certain amount of power, or when we talk about the value of beta, that is always based on a particular effect size, let's put it that way. And so when we get into talking about power analyses, for example, where we determine the sample size necessary to have a certain amount of power, we always have to specify as one of the arguments to that analysis, or arguments to that power function, the desired effect size that we want to be able to detect with the given amount of power that we've specified. And so we would typically, and so that is how we come up with a given sample size for a particular situation. Now again, I want to reiterate what a p-value is and how we use it. All right, it's very important that we understand exactly what a p-value is. We don't want to misrepresent it or misunderstand it. And so the p-value is a measure of how likely the observed results are if conditions of the null hypothesis are true. So this is, the p-value is actually it's a conditional probability. In particular, it's the conditional probability, it's the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed if the null hypothesis is in fact true. So conditional on the null hypothesis being true. And again, when we talk about at least as extreme, what we're talking about is in the direction of the alternative hypothesis. Now, I want to point out that it is not the case that the p-value is not the probability that the null hypothesis is true. That is a common misconception, it's a common misunderstanding, and it's a common misinterpretation when people write up results or when they read results. We need to make sure that we do not interpret a p-value as the probability that the null hypothesis is true. The p-value is specifically the probability of observing a value of the test statistic at least as extreme as that which has been observed if the null hypothesis is in fact true. Now, if the probability of observing a value of the test statistic at least as extreme as that which has been observed if the null hypothesis is true is small, right? If that probability is small, what that's telling us is that the observed results that we've seen are not likely if the null hypothesis is true. And you'll remember that what we're looking for here is to see whether the observed data are consistent or inconsistent with the null hypothesis. And if the data are inconsistent enough, then that's going to lead us to reject the null hypothesis. Well, translated into terms of the p-value, what that means is that the smaller the p-value, the less consistent the data are with the null hypothesis. In other words, the smaller the p-value, the more inconsistent the data are with that null hypothesis. And so that tells us how we are to draw conclusions using the p-value. Specifically, we reject the null hypothesis in favor of the alternative. In other words, we conclude that the null hypothesis is false and that the alternative hypothesis is true if the p-value is small. How small? If it's less than or equal to alpha, which is the significance level used for the test. Now, we have talked about, in talking about the general characteristics and components of a hypothesis test, we identified as part of the hypothesis test statistics and critical regions. All right, and we discussed how to make decisions about hypotheses using the test statistic and the critical region, the rejection region. Here we have, in talking about p-values, another approach to using or to drawing conclusions in the context of hypothesis testing. And this approach using p-values is completely 100% equivalent to using the test statistic and rejection region method. In fact, rejecting the null hypothesis, if the p-value is less than or equal to alpha, is equivalent to rejecting the null hypothesis if the test statistic falls in the rejection region. So that is what a p-value actually is, and this is how a p-value is used. Now, almost without exception, when you're writing up your results for a research article, or if you're reading somebody else's research articles, the results are summarized, or the rejection criteria or the significance information about the experiment are quantified by the use of p-values. So in other words, the p-value method for making decisions is used almost invariably in research articles instead of the test statistic and critical region method. And the reason is that if you use the test statistic and rejection region method, then the rejection region depends on whatever significance level you use. And so if you were to use that in an article, then everybody reading your article would have to use that same level of significance. On the other hand, if we use the p-value method, then people can they can choose their own significance level to evaluate the significance of the results. And so that's really the primary reason why the p-value is used. It's equivalent to using the test statistic and critical point, or critical region method, but the use of p-values allows each consumer or reader of a study to draw their own conclusion based on a level of evidence via a significance level alpha of their own choosing. So see, it allows people to use their own level of significance, all right, that they want to use, that they choose to use in evaluating a research study, and that level of evidence is selected or is contained within the significance level. Now let's talk just briefly about that, the relationship between significance levels and levels of evidence. Here is how this works. Using a smaller significance level is equivalent to requiring stronger evidence against the null hypothesis in order to reject it. On the other hand, using a larger level of significance is equivalent to requiring less evidence against the null hypothesis in order to reject it. And so when you're doing research, you come up with some results and you write up those results in a research article. You may choose to use a 0.05 level of significance in order to determine whether or not the results are significant. Now, a reader of your paper may require more evidence than you, and to do that, they would require or they would use a smaller significance level. For example, they might use a 0.03 or a 0.01 level of significance. On the other hand, if somebody used a larger level of significance, for example 0.08 or 0.1 even, then they would be requiring less evidence against the null hypothesis than you were using in order to reject that null hypothesis. So this has been a review of the general process of hypothesis testing, the components of a hypothesis test, characteristics of a hypothesis test, relationships between those characteristics of hypothesis tests. we'll be obviously using these kinds of things as we go throughout the course.